Thank you very much for the very kind and generous introduction. It's a real pleasure to be back here after 32 years of studying at IISc, and the campus is still as beautiful and green as ever. Thanks, Arindam. It was a pleasure to be your mentor and advisor. One of the tasks of the advisor is to gently correct any missteps and make corrections. So I'm not an ACM fellow. I'm actually not even a member of ACM, but I'm an AMS fellow, American Mathematical Society. But again, thanks for the introduction. So this is a tribute to, again, thanks for all the taxis that the amazing hosts amazingly organized for all of us, although some of us declined such help this morning. It has some other role in the talk. It was so it just happened to be a nice coincidence. So the topic I'm going to talk about is at the intersection in some ways of several fields: combinatorics, theory of computing, statistical physics, and also communication networks. So let me start by saying what the so-called hardcore model or hard lattice gas model is on the integer lattice. The first slide said on ZD, d-dimensional hypercubic lattice. For the most part, I'll restrict myself to the two-dimensional case. And I will mention briefly what's known in higher dimensional case. So what is this model? Ignore the colors for a second. We have an n by n grid as a finite piece of Z2. You can also think of the infinite Z2. But observe that this is a bipartite graph. And so the configurations we're interested in are the so-called independent sets, right? So an independent set in a graph, as we all know, is a subset of vertices with the property that two vertices in the independent set should not be adjacent to each other, right? So ignore the color. So all the red or blue together form an independent set, let's say. So notice that no blue is next to each other, or no red and blue, any of those is next to each other. So that's an independent set. Incidentally, please raise your hand and ask any questions. Feel free to interrupt me if something is not clear. What we're going to be interested in is a probability distribution on the set of independent sets of typically a finite piece of the infinite grid. And it is quite interesting to consider uniform distribution where each independent set, including the empty set, is given the same weight. But we're going to have a parameter lambda that's a positive real, and we will instead consider the more general case of associating each independent set with some weight lambda to the size of the independent set. Okay, so if I have 4 plus 5, 9 vertices here, the weight for this configuration is lambda to the 9. Okay. And if it's a finite piece, I can always sum over all possible configurations, the weights of them, to make it a probability distribution. Okay, so that's the model. And why hardcore or hardcore lattice? So in physics, this was introduced as an idealized model of gas. So the occupied particles are gas molecules, and the model is such that somehow the radius or the size of the sphere is just large enough that you don't have space to put two next to each other. Okay, so that was sort of one motivation. And why, so that's the lattice gas model. Why hardcore? So people might be familiar with Ising model and some other statistical physics models where you don't forbid any configuration strictly. Here we forbid configurations that have two vertices both occupied next to each other. So that's a hard constraint. So the soft constraint would be you take all possible configurations, but then you penalize for having two vertices next to each other. Here we're penalizing in the most severe way. Okay, so that's where the name comes from. So physicists observed a long time ago, I'll show some dates in a second, that there's a sort of phase transition in the following sense. If you look at this model for small lambda, you see a certain behavior, and as you increase lambda, you see a different behavior. Okay. And the question that's still unresolved is, where exactly does this happen on the two-dimensional lattice? Okay, so I've already disappointed you by saying it's unresolved, and so I will show you what we know so far. What's the best known until today? So now let me mention the colors. Okay, so the red and blue, as I said, this is a bipartite graph. So we can consider, say, the origin to be the red parity. So we can a formal way to say what a vertex, when a vertex is even or odd, is if you represent a vertex by its coordinates, because this is in Z2 or ZD more generally. So it's a sequence of d integers, in this case 2 integers. You can say the sum of the two coordinates being even will make it even parity. Sum of the two coordinates being odd is odd parity. Okay, that's one way to say this is the bipartite graph. And so it turns out for small lambda, in this case for the two-dimensional as if lambda equals 2, and this is an 80 by 80 grid, this is what it looks like. What looks like? So if I were to take a random sample from this distribution where each independent set has lambda to the size and lambda is given to be 2. So this is favoring larger independent set because lambda is larger than 1. If lambda were equal to 1, then nobody is favored because of their size, right? So lambda bigger than 2. It looks sort of mixed. There is no real majority one way or the other, but once you go to lambda as high as 5, it's clear that it seems somehow more red than blue. And so physicists are interested typically in understanding whether, yes. Yeah, so red is, so both colors represent the fact that that vertex is in the independent set. Red is because it's a bipartite graph, this is occupied even vertices, let's say, and blue is occupied odd vertices. Okay? Any other questions? So again, in this picture, so if this is red, this is say an even vertex, it's unoccupied. This is an odd vertex. So if this is even, then those 4 blue neighbors are of the other parity. And of those, in principle, you could have all 4 of them occupied, but 2 happen to be occupied. If this were to be occupied, you couldn't have them. That's the model. So there's a conjecture that there is in fact a lambda critical. There is a precise value of lambda, a real number, so that below that you don't really see any bias in how many reds are occupied versus blue. So it's sort of a mixed state. Whereas if you go above that, then it's going to be either mostly red or mostly blue, one of the two, on the infinite line. If a way to finitize and understand this problem is to say, let me insist on not the free boundary, so-called free boundary, instead a fixed boundary which says for a large n by n, say 80 by 80, I insist that all the vertices on the boundary that are of odd parity are occupied. Okay, and now I want to study this conditional probability distribution. Oops. Press something here. Okay, I don't know what happened. Yes, so there's a so here's conjecture 1 or conjecture 0. We don't know whether such a lambda critical exists. Okay, this is open, even in 2 dimensions. Whereas for many models, Ising model, Potts model, and so on, in the square lattice, it's known precisely. And for the Ising model, it was known due to Ansager many years ago, in the 50s or so, and then Dominiel Copin and his advisor showed for all higher number of spins, Potts model and so on, in the square lattice. So those are soft constrained. This is a hard constrained model. And unfortunately, part of the difficulty is there is no monotonicity, meaning if I show to you that for lambda equals 5, it looks like that, namely that there is bias based on what boundary you put. It doesn't follow that for lambda 5.1, the same behavior holds. We don't know that. That's what I mean by monotonicity. However, any proof that establishes that such a bias occurs for any lambda, the proof works for any higher lambda. So that's how we know that I'll show some numbers in a second, that for certain value and above, in fact, you feel the effect of the boundary, meaning if you put odd boundary at n by n, no matter how large n is, if the origin happens to be of the odd parity, it's more likely that origin is going to be occupied. Whereas if I put the even boundary and the origin is odd, it's less likely. Okay, so that's how you can finitize the problem rather than having to study on the infinite lattice. So let me skip that. This is about, one has to define what it means to take such a measure, so-called Gibbs measure on the infinite lattice, and it's done by taking a sequential limit and a weak limit for larger and larger boxes that eventually extend to Z2 or ZD in general. But as I said, for our purposes, we can think of just the finite version. So for the infinite, the question is, do you have, you can take consistent boundary conditions that give you one Gibbs measure. The question people are interested in is, do you have only one or do you have multiple? It turns out that lambda critical, whose existence is conjectured, has to do with up to which point you have a unique measure and beyond which you have multiple Gibbs measures. So let me move on. Okay, so I've already said this. So if I put this red boundary and the origin happens to be red, okay, so I can say, given, so this superscript says red boundary versus blue boundary. Okay. Turns out if I put the red boundary, then the origin which has the right parity, meaning the parity that matches the boundary, is more likely to be occupied when I take this lambda weighted probability measure. Whereas if I put blue, it's less likely. So as is often common in physics, while the existence of lambda critical is not known, they boldly conjecture that it's actually 3.796, and there are papers written where further digits are specified and so on. And this is made quite a while ago, as you see. There's certainly one paper where some of the first couple of digits appear by Gaunt and Fisher. And as I said, we don't know the existence of lambda critical. But you can certainly derive results that say, if lambda critical were to exist, it's above certain value and below certain other value. And that's going to be the focus of this lecture. So what's known from one side, let's say we want to show that you don't feel the effect of the boundary up to certain lambda, okay, from below. So there's a classical argument known as the Brownian uniqueness condition that basically localizes the problem and looks at a vertex and says, what is the effect of the bound, just the neighbors of that vertex? Okay, you can do some conditional calculation and get a result that for the two-dimensional lattice gives something like 1/4. More generally, for the d-dimensional lattice gives something like 1/2d. That shows if you're below 1/2d, certainly in ZD, you don't feel the effect of the boundary. But already for lambda equals 1, it's challenging, which is, an interesting case because that's unweighted, every independent set being treated uniformly and so on. And there's been a series of results, and best known, I think, so there's quite an impressive piece of work by a student of Alistair Sinclair some years ago, Dror White's 2006. I'll say Dror White's result in a second. That gave a certain very nice extremal result for this problem. So with my colleague Eric Vigoda and some students and a postdoc, Jinwoo Shin, we refined that argument and the technique that Dror White's introduced by taking into account the fact that we have Z2 or ZD in general. So including the specifics of the square lattice, we could go quite a bit beyond and get something like 2.35. And that was then further optimized, let me say, by Piyush Srivatsava primarily, and his advisor Alistair and other co-authors in getting to the best known today, which is 2.538. Okay, so from below, what we know is if if you consider the lambda weighted independent set for lambda below this number, then you don't see the effect of the boundary. Okay, so again, physics conjecture is around 3.796, and we are at 2.53. They also have a result that says using these methods, we're unlikely to go above, some value. I forget. I'll probably have in the next slide. Okay, that's what's known from one side. So on the other side, again, there's an argument of Dobrushin, or I'm not sure, it should have been maybe a Peieris type argument that gives some large constant, okay, for 2 dimensions, some large constant. And Christian Borks and David Galvin, when David Galvin was a postdoc at Microsoft Research, did the computation and came up with something like around 300, which is way larger than what's expected. In higher dimensions, so I'll say briefly some connection to sort of theory of computing algorithms type problems, in particular dynamics that converges to the correct distribution, the lambda weighted distribution. And there's a close connection between when you have multiple Gibbs measures and when this local dynamics mixes quickly or slowly. So I thought I could cheat and show that for this local dynamics, the mixing is exponentially slow for a very small value of lambda, such as lambda equals 5. But turns out, that was equally difficult, and actually our results for that problem were worse than what we could do, what we know now for the original problem. And for higher dimensions, what we showed with a bunch of people who were all visiting Microsoft Research at the time is that for lambda, which depends on the dimension, but unfortunately exponentially in D, exponential dependence on D. If lambda is above that, then when you do the dynamics, which is simply the following, you pick a vertex at random. So you have an independent set at the moment, you pick a vertex at random. If it's in the independent set, then you remove it with probability 1 over 1 plus lambda. Turns out that's the right way to. If it's not in the independent set, consider including it with probability lambda over 1 plus lambda. The reason I say consider including it is one of the neighbors might be already in it, so that means you reject that step. But if none of the neighbors of the chosen vertex is in the independent set, then you include it with lambda or lambda. And so how quickly, it's easy to show that this dynamics converges to the lambda weighted distribution on any finite n by n piece, and more generally on any graph. Okay, not necessarily the square lattice. But the question is, up to what value of lambda does it mix quickly versus slowly? Okay, so it's a related question, and there are results there as well. So the best known we could get is now in some work with Antonio Blanca, and I forgot the first name of Chen, who's an undergraduate student working with David Galvin, with Dana Randall, my colleague, and myself, is around 5.35. Okay, so the results are now between 2.53 and then 5.35. And basically that's the most we know now. And unfortunately, disappointingly or encouragingly to people who want to think about it and come up with new techniques, we can also show that these techniques are not going to go much further than what we've done. You really need to come up with something different. Okay, if you want to get between 3 and 4, you need something different. So here's a very nice connection. I'm not going to use very much of this next set of results, next couple of results, but this says, okay, why am I wasting the time of theoretical computer scientists? Or what's the connection? The short answer is basically there's 2 very impressive sets of results, 2 PhDs from UC Berkeley. So Christos should be very happy, although he moved recently to Columbia. So let's look at estimating the number of independent sets given a graph. Okay. It's hard to prove computational complexity type results for any specific graph, right? You can say, well, given an input that's a graph and the parameter lambda, or just the graph, when can you tell me how many independent sets there are? Of course, we all know this is a very difficult problem. Sharpie hard even for maximum degree 3 or something. So the next question is, can we approximate, right? So by the way, Z sub G is that denominator that we can use to normalize the weighted distribution into a probability distribution. Okay, so if lambda were equal to 1, this Z sub G is the same as the number of independent cells. So there's some standard terminology. FP-TAS, I think it's called now, fully polynomial deterministic scheme versus FP-RAS, which is randomized approximation scheme. And standard notion is that if Z sub G, which is say the total number of independent sets, is what you're interested in, can you come up with an algorithm that outputs an estimate that's within 1 plus or minus epsilon, right? In polynomial time, in the size of the graph or number of vertices and 1 over epsilon. And again, it's standard in this business to say because of certain self-reducibility condition, sampling and approximating in the sense of FP-TAS or FP-RAS are equivalent. And so now if we consider sampling, this you get the dynamics that I already talked about. X sub T is the current independent set. You either include the chosen vertex with probability lambda or 1 plus lambda if it's a valid configuration, otherwise you remove and so on. Okay, so I've already talked about this. So here, yeah, this slide is basically the story of connection to complexity. So rather than looking at the square lattice or the integer lattice, if you ask for the analogous question on the tree, infinite D-branching or delta branching tree, okay, so delta equals to 2 would be every node has, except the root has 2 children and so on, right? Because we are on a tree, you could do recursions and figure out explicitly when you have unique versus multiple fixed points and so on. So you can answer this question. And Frank Kelly is one of the people from communication networks who considered the model and derived this. There were other people who independently identified the value. Okay, so for this T sub delta for the tree, turns out there's a closed form expression for lambda critical. Okay, so what's the significance of that? Alan Sokal conjectured and Dror-Weitz proved it. What's really amazing is that it turns out this value has a certain significance, namely up to this lambda, every graph with maximum degree delta in fact has a unique Gibbs state. So tree is the worst case in a sense over all graphs of maximum degree delta for this question. Okay, and Dror-Weitz proved that with an extremely interesting reduction to tree. He constructed a tree of self-avoiding walks or paths on any given graph, and it's a special tree of same max degree that he constructed, and he transferred the problem of whether you feel the effect of the boundary or not on the original graph to a slightly more difficult problem, more difficult question, technical term being strong spatial mixing, while weak spatial mixing corresponds to uniqueness or multiplicity. And he showed that in fact strong spatial mixing also holds up to that lambda critical on the tree. What's even more remarkable is that so that was one PhD thesis. Alan Sly, who was Elchanan Mosel's student, showed that in fact it's NP hard to go beyond that in terms of approximation in general, given an arbitrary graph. So we have one lambda critical that's coming from some statistical physics or communication networks, whatever, or combinatorial problem of independent set, and computational problem up to what lambda critical can you do that. And it turns out the transition is identified by studying that on this delta branching tree, but that coincides precisely with this computational hardness, or below that it's easy, above that is hard. So Alan Sly first showed that slightly above that, between lambda critical and some epsilon delta is hard, but then by him and others it's been, people knew that was just some shortcoming of the proof technique, and it's been extended to for all lambda above that. Okay. So coming back to the square lattice, White's result gives us, if I were to plug in delta equals to 3, I believe, because I want to think of the square lattice case as delta equals 3 or 4, I forget. It should be 4. So the maximum, the square lattice, we think of it as 4 regular or maximum degree 4, it gives us 3 cube over 2 to the 4. It gives us for free that up to that value, we don't feel the effect of the boundary, because on the tree you don't. Okay, so that gives you something like 27.6. What we did was, we said, well, okay, let's look at his proof, and let's analyze the particular self-avoiding walk tree one gets, or some approximation of that for Z2, or for the n by n grid. Okay, then, and then we had to do more analytical work, but the basic idea is to say that that's true for all graphs of maximum degree delta, all graphs of maximum degree 4, but the square lattice is it's a particular special case, so we went beyond that, and that was basically how we got to the 2.35 and so on. Okay. There were other works, related works in between, but Drawers is this number, and what are the conjectures of it. So let me move on to incidentally, the way we prove this also shows that for the dynamics you have fast mixing, in fact basically optimal mixing, order n log n up to that value of lambda. Okay, any questions before I go to the other side? Yeah, so it's not, so Drawers' work is not particular to the d-dimensional lattice. So take any delta max degree graph. As I said, so one thing I didn't mention is that it turns out to approximate the partition function, the total number of independent set or z's of G, it's sufficient to approximate the probability that a particular vertex, say the origin, is in the independent set. The reason is you can do a telescoping factorization. So you can, what happens, ZG can be written as ZG divided by ZG minus 1 vertex, and then ZG minus 1 vertex 2, right? So each of those factors now is a marginal of a vertex in a particular graph. So now you say, okay, let me look at a particular graph on a particular vertex of any graph, and I'm going to consider all self-avoiding paths starting from that vertex. And those paths can be written in a systematic way on a tree, where a path that extends a subpath is going to be, the descendant of the previous path. So that's how he constructs. You get a max degree one, but then he artificially includes some additional vertices whose occupancy is fixed one way or the other to get an actual delta regulator. That's roughly. And as I said, sorry? Yeah, D is delta. Or actually, delta is 2D, because in Z2, the degree is 4. Right? Yeah. So D is the dimension. So 2 times D is delta. And we basically said, well, what are the kinds of paths you get for the lattice? And we pruned the tree, the worst case tree that Drawers. Okay, I don't have too much time, but let me try and say a little bit about the other side, namely phase coexistence. How does one show that one feels the effect of the boundary if all the red vertices are enforced to be in the independent set, no matter how far away from the origin you are, right? That's what's surprising. You still feel the effect of the boundary, provided lambda is above some value. So there's a little story here in physics for the Ising model. Lenz, I believe, was the advisor of Ising and asked Ising to show that there's phase transition on for the Ising model on ZD. And the student Ising studied it on Z, on the one-dimensional case, showed that indeed, in fact, one-dimensional case, there is no phase transition. I mean, the boundary is just two vertices, right, if you have a line. And he said, oh, no, there's no phase transition on ZD for any D. So later, with the so-called Peieris, but still, Ising managed to get his name attached to this model. But then it was shown using the so-called Peieris argument that in fact, one dimension is the anomaly. In all other dimensions, you do have this phase transition. And so the idea is as follows. At a very, sort of 30,000 feet level idea, you want to show when you put the blue boundary, as I've done here, okay? So all the blue vertices on the boundary are occupied, meaning I enforce that they're always in the independent set. The origin is, say, the red vertex, right? I would like to show it's unlikely. For this to happen, it's unlikely. It's sufficient for me to somehow distinguish between the two marginal probabilities, the two cases being blue boundary versus red boundary, always looking at the origin. So we know, right, from basic combinatorics, if you want to show the size of one set is less than or equal to another set, it's sufficient to provide an injection, right, a map that says two vertices are not mapped to this, two points, x and y. If x is different from y, f of x is different from f of y. That shows size of the domain is less than. Here, we want to do something like that in a weighted sense. We want to show the weight of configurations where you have the blue boundary but red occupied, okay, is much smaller than if I were to put red boundary and look at origin occupied. Okay? So it's sort of this weighted injection type argument. And the way it's done in this, due to Peieris to begin with for Ising, is you say at some point the parity must have switched. So you construct a connected graph containing the origin that's occupied, okay, with this distance 2 graph. So these two are connected because that's the closest you can be, red occupied, and be a neighbor. At some point, it must switch to blue because the boundary is blue. So there's a formal way to define what's this contour or a fence around all red occupied that are connected, and then it must leave a gap of 2 vertices for you to switch parity. Okay? So what happens then, I'm running out of time, excuse me, is that, so you can make so to get this injection type idea, you can go from red being occupied to not occupied by shifting each of the ones inside the contour, each of the red occupied, in one of the directions. Okay, so pick, in this case, left direction. What you do is, what you realize is that the contour gives you some free space, so you can map all these reds to the left. Okay, that's how you go from red occupied to red unoccupied. This is the same as saying, if you were to have a red boundary and then red occupied or something. Okay, it's just equivalent. See, now I've transformed from having red occupied to red unoccupied, which is the more likely because the boundary is blue. Right? So I've gone from red zone to, this is how I've erased it. So of course, that's a high level idea. What you have to show is not too many on the left mapped to the same. So it's not going to be a strict injection, but because we have weights, we show that this is how I map to the codomain, but as long as I show not too many map, I'm okay. Also notice that the weighted business tells me in the calculation, so if I have a contour of length 4L, right, so the size of the fence is 4L, then I pick one of the 4 directions, okay, in Z2, so I pick the left direction. It's easy to show I can gain L new vertices if there are 4L on the fence. Okay? L because 1 by 4 because of 4 directions. So I've gained in weight 1 plus lambda to the L in going from left to right. Okay, so this one-to-many map has this weight, because why 1 plus lambda to the L? Because I could choose to put all L vertices in there, but and so that's 1 plus lambda to the L. If you were unweighted, lambda equals 1, it would have been 2 to the L, all possible subsets of a set of L vertices. In the lambda weighted case, this is occurring. So let me wrap up and say, so basically, that's the basis of this so-called Peieris argument, and it gives us a way to say if there's the blue boundary condition, then the red vertex at the origin, the fact that it's, the probability that V is in the independence is unlikely, but it gives you a quantity like this. It reduces our problem to a combinatorial problem of saying, okay, how many contours are there of a given length? Okay, because that's also relevant. How many contours? And then for each contour of a given length, it's this 1 plus lambda raised to L. That's the way. Okay, this physicists call this entropy versus energy. Entropy has to do with number of such contours. Energy, how much each contour is worth. So when I say these techniques basically run out of gas, we've milked the most we could using this kind of technology. So the combinatorics here resulted in characterizing the kind of contours we have by considering a slightly rotated lattice and then placing vertices on the middle of the original edges, so like a subdivision. And so the dark black region you see is what we call a taxi walk, and that's the reason for the taxi picture to start with. So it turns out the property these have is that each time you go either straight or turn. Whether you turn right or left depends on whether you've taken even number of steps or odd number of steps in going straight. So taxi, if a taxi guy does 3 right turns, consecutively, then you get suspicious because you think, well, they could have gone straight, right? Why did you go straight, make a right, and then a right, and then again a right? So we don't do that in these walks. So for that reason, we call these taxi walks. And we estimated how many such walks there are of length L, and I'm skipping the details because I'm out of time now. So basically, our results follows by saying somehow counting these taxi type walks more precisely in getting to the best known bounds of that. Let me stop. Okay. So maybe as sort of the quick summary of that, and this is saying we can also get results similarly for the mixing question. That if lambda is above certain value and then by in box. So the results here are slightly worse. Then the dynamics is slow on the torus, slightly smaller value. Here are some natural questions. So on high dimensions, so for D large, on ZD now we know much better. So this, as I said, Dobryshin's argument gives you something like 1 over D or some constant over D. And there's nice work following initial work of Jeff Kahn and David Galvin by Ron Peled and Wojtek Samati that gives 1 over D to 1/3. So for large D, this is the open problem. Can you show it goes to 0 with D, but with what exponent? And of course, we don't know the monotonicity or existence of lambda critical. And I have some ongoing work with Will Perkins, my former postdoc, and Piyush Srivatsala, that's looking at this model where we assign 2 different values for the even vertices and odd vertices, lambda even, based inspired by a conjecture of Vandenberg-Epstein. So they conjecture that as long as they're different, in fact, there should be a unique Gibbs measure. You shouldn't feel the effect of the boundary because you broke the symmetry. In 2 dimensions, it's known that that's indeed the case, but in high dimensions, it's known partially, as in it's known the set of values of lambda is countable where this happens. But it's not completely nailed down, and we are looking at this on a tree and other right now. Okay, thank you.